All right. Welcome everyone to the session on Folsom Services. We have 5 papers in today's session, and we're going to start off with the first paper presented by Masood Rahman from Dalhousie University, which is the forgotten role of search queries in IR-based bug localization. Go ahead, Masood.
Can you guys see my screen?
Yeah, absolutely.
Okay. Good evening, everyone. Welcome to my presentation. So my name is Masood Rahman. I'm an assistant professor at Dalhousie University. And the work that I'm going to present is a collaborative work with Polytechnic Montreal as well as University of Saskatchewan. And these are my co-authors. So this talk is about query reformulation in the context of bug localization. And many of you might be already familiar with that, but let me try to provide a bit of little overview. So let's say this is a bug report, and we want to identify this buggy code using the information from this bug report. So what many of the techniques were doing over the last decade was that they will use this whole bug report as a kind of search query, and then they will execute this query with some kind of code search engine, which is sitting on top of the code base. And then they will try to retrieve the buggy code. And the expectation is that the buggy code will be retrieved at the higher position of the ranked list. But as you can see, that always does not happen, because this bug report is not designed to be used as a kind of search query, because it has like 127 words. So what many folks did, they tried to identify a subset of keywords from these 127 words, and they call this subset of keywords as a kind of query. And then they will try to execute this query, and then they will try to retrieve the buggy code at a higher position. So I'd like to focus on this part, that is the query reformulation in the context of IR-based bug localization, and we'll try to drill down on this topic a bit more. So we have 3 research questions in this work, and I'm going to provide a bit of overview on the 3 research questions that we have. So in the first research question, we try to evaluate the performance of different kind of state-of-the-art techniques in the context of IR-based bug localization. And what we found is that the state-of-the-art techniques are not sufficient, especially for 1/3 of the bug reports. So we found that, let's say, around 34% of the bug reports in our data set, for which the state-of-the-art techniques were not sufficient. That means they are not able to identify the buggy code within the top 10 position of their result list. So which is a bit shocking. So what we did in the second research question, we tried to identify that whether this 1/3 of the data set actually contains some meaningful keywords in their bug report. So if the bug report does not contain the meaningful keywords, then there is no point of query reformulation, right? So what we did, we used genetic algorithm. We also used a ground truth information to identify the optimal search queries from that bug report. And to our surprise, what we found is that although the baseline technique, that is the pre-processed version of the bug report, as well as the state-of-the-art technique, are failing to identify appropriate keywords from this 1/3 of the bug report, those bug reports actually contain some meaningful keywords. And we are calling that optimal search query. And those optimal search query actually lead to very high performance in the context of IR-based bug localization. So now what we have optimal search query, and we have also non-optimal search query. So in the third research question, we try to differentiate between optimal and non-optimal search queries using machine learning technique. And we used random forest algorithm, and the performance was pretty interesting. So we are able to differentiate between optimal and non-optimal search queries using close to 80% precision and 80% recall, which is interesting. And when we did a bit of feature importance analysis, what we found is that the optimal query and the non-optimal search query could be quite different in terms of different properties, like the keyword frequency, then their entropy, then the keyword location within the bug report, as well as parts of space. And this is a kind of our actionable insights from the third research question. What we found is that the optimal keywords are less frequent than the non-optimal ones within a given bug report. Then optimal keywords are less ambiguous than the non-optimal ones, and we use entropy to determine that. And we also found that optimal keywords are more likely to be found in the body section than in the title section. And we also found that optimal keywords are more likely to be nouns than the non-optimal ones. So since we have a very brief time, so let me provide the takeaway message. So what we found is that around 1/3 of the bug reports for which neither the baseline technique nor the state-of-the-art technique are sufficient to identify appropriate keywords from those bug reports for bug localization. But those bug reports actually contain some meaningful keywords, and we identify that using genetic algorithm. And those optimal keywords lead to very high performance in the context of bug localization. And then we also try to differentiate between optimal and non-optimal search query, and we found that they could be quite different in terms of different properties. And we apply this actionable insight, and we also were able to improve the performance of baseline and state-of-the-art techniques significantly. And these are the open questions. Okay, guys, I'm done. Thank you.
Thank you, Masood. Moving on to the next presentation by Han.
Hello. Hi, can you hear me?
We can hear you.
Oh, okay. Sorry about that. I'm not sure what happened to the camera. It was working, but it's just go back on my
You
now.
can share your screen.
Okay. All right. Should I start now? I'm presenting it, but I'm sure why it's
Yes, you are presenting.
oh, okay, cool. I'll just start. Oh, what's going on? So hey everyone, thank you for coming to this session. My name is Han Wang. Today I'd like to present our research, which is software engineers' response to public crisis lessons learned from spontaneously building an information COVID-19 dashboard. The outline of this paper. Well, as we all know that the COVID-19 virus has spread quickly around the world, governments have taken actions such as lockdown.
If you're going to the next slide, that's not showing right now.
Yeah. Oh, it's not showing. I'm not entirely sure what happens. Let me just reshare it. Maybe
You can advance the slides in the presentation screen. It's okay.
yes. Is it working now?
Now it's okay.
Yeah, that's good.
Okay, cool. Thanks. Sorry about that. Okay, so we all know that COVID-19 virus has spread quickly around the world. Government taking actions such as lockdowns, border closures, working from home, which have influenced like basically everyone's life all over the world. And at first, we know little about this virus. Therefore, people are urged to get the latest update and information about this virus. Well, there are several ways to gain such information, for example, from the government daily release, the social media such as Facebook, Twitter, YouTube. There's also TV news on that. However, they have their shortages. Therefore, COVID-19 information dashboards are developed. In our scenario, we developed the COVID-19 AU website, which is a COVID-19 dashboard for Australian people. Here's an overview of this dashboard. It contains a homepage which illustrates the key data and visualizations. The information page contains the official instructions from government and trusted organizations, and also the news page, which shows the live news from large news groups and official Twitter accounts. Here's the project characteristics. So we published the website on mid-March 2020. It is one of the first COVID-19 dashboard in Australia. The team consists of over 200 volunteers from 12 different nations. Most of them are undergraduate, graduate students from the universities in Australia. And here's the impact. We have a large number of users and page views during the time. And although most of the users are from Australia, there are also some of them from other 184 different countries and areas all around the world, as they have friends or family members in Australia. And here's an overview of how we developed the dashboard. But most importantly, with our first-hand experiences and theories in software engineering area, we summarized 9 lessons that are highly related to the pandemic. We categorized the lessons into 3 aspects: developers, researchers, and for example, here's the first lessons for the developers, which is be careful about the sensitive data. So for example, we were using the old design, which is the pinpoint design. We use the pinpoint to represent confirmed cases in certain area. Then we received the feedback from users that one of the markers was actually pinpoint on his farm that he's definitely not happy with. We also received some feedback like the pinpoint was pointed into a national park, which really confused the users whether there's a confirmed cases in the park or not. Therefore, we changed our design to the right-hand side one, which use different shades of red to represent the confirmed cases in the area to avoid the ambiguous and the misunderstanding. And there's also other lessons like use domain-specific terms, keep user calm during the pandemic, and also develop different features for different phases of the pandemic. Well, for the researchers, during the development of the dashboard, we have collected user feedback and their overall usage activities through Google Analysis. And therefore, we come up with the following 3 lessons for the researchers. And since most of the volunteers are university students, we summarized their experiences, conducted surveys, and also listed the suggestions that may help the software engineering instructors to teach as the principles and concepts during the pandemic throughout the project-based learning. And to summarize, this is a timely social good project for developing a COVID-19 dashboard. This is also a case study from which useful insight may be drawn on how to properly understand and design for human values as the 3 roles a software engineering can play. And in the future, we hope to keep improving the dashboard, and also we try to develop a dashboard template for emergency disasters, for example, earthquake, bushfire, or tsunami. And thank you. That's all I'd like to present today.
All right, thank you. Moving on to the next presentation on fault localization via efficient probabilistic modeling of program semantics.
Okay, now hello everyone, I'm Yichen Wu from Peking University. I'm glad to present our work fault localization via efficient probabilistic modeling of program semantics. Testing-based fault localization has been a research focus in software engineering for a long time. The inputs include a faulty program and a set of tests with at least one failing test. The output is the specificity score of each program element. Among large body of fault localization research, a central focus is coverage-based fault localization. For example, the most famous technique, section-based fault localization. The idea is that an element covered more by failing tests rather than passing tests is more likely to be faulty. However, how a buggy element causes the failure is more complex. Here is an analysis model named PIE. First, the tests need to cover a buggy element. Second, the buggy element results in errors in program state. Third, the errors are propagated to the output. Finally, the errors are captured by an assertion. From the analysis, we can find coverage-based methods only consider the first condition. But letter 3 can also be very important, and they correspond to the semantics of the program. So here comes the question, how to model the letter 3 conditions? To overcome this problem, different approaches have been proposed to take the letter 3 conditions also into consideration, such as mutation-based fault localization and anxiety debugging. However, these approaches take the full program semantics into consideration, so the analysis is inevitably heavy. To this end, we propose a novel fault localization approach, SmartFL. To analyze how a fault is to the current test results, we model the probability of each statement introducing and passing an error. Such analysis also requires efficiency, so we abstract the full program semantics. We introduce random variables to represent the correctness of each statement and runtime variable value. Also, we transform program semantics into probabilistic constraints between random variables. Here, let's see a run example of our approach. We have a simple function foo with 2 tests. It is buggy in line 3. The condition should be a less than 2, but now it is a less than or equal to 2. And we have 2 tests. Both pass test and fail test follow the same child, line 3, line 4, and line 6. Now let's see how our approach models this program. We introduce some binary random variables. Si represents the correctness of line I, and Vi represents the correctness of variable value defined as line I. First, for the prior probability, we set each statement to be 0.5. The next few formulas are about pass test, and we have similar formulas for fail test as they follow the same child. For the input, we can know V2 must be correct. Then, for line 3, we can say if S3 and V2 are all correct, V3 must also be correct. However, if one of them is wrong, we think V3 has a 0.5 probability of being correct. It is because line 3 is a Boolean expression, and it is likely to get the correct result, even if the input or the statement is incorrect. For line 4, one difference is that we take V3 into consideration because that condition value controls whether line 4 is executed. Also, the operator of line 4 is plus, so we set the incorrect to correct probability to 0.01. Now we want to calculate the posterior probability of S3 and S4 being wrong after we observe V4 key is correct and V4F is incorrect. And the result shows that S3 is more likely to be wrong according to our model, which is reasonable. In our experiment, we choose 4 projects from the Fast4J as benchmark, 222 faults in total. We select OCI and DStar from SDFL, Metallics and Muse from MDFL for comparison. For the results, we can see SmartFL performs better than other methods, especially on top 1 at statement level. Also, the average time of SmartFL is much smaller than MDFL method. In summary, here are the main contributions of this paper, and you can watch the detailed video on YouTube. Our tool and evaluation data are publicly available on GitHub. Welcome to follow our work and get in touch with us. Thank you.
All right, thank you. So moving on to the next presentation on adaptive performance anomaly detection for online service systems via pattern sketching.
Okay, let me try to do the screen sharing. I have some connection problem. Hey, I'm wondering, would it be possible to move on to next one first? Because I need to switch the permission control.
Okay, so fine. Let's move on to the next one, which is effect porting energy-aware applications to shared environments by Timur.
All right, is everyone able to see my screen okay?
Looks good.
Wonderful. All right, so my name is Timur. I'm going to be presenting our work from SUNY Binghamton on eFlect, which is a framework to port energy-aware applications to shared environments. So to start, energy-aware applications are a really simple concept. It's some application that has knowledge of their energy consumption. And so this is a really important feature for green software engineering because it enables things like energy adaptive software design, energy profiling and debugging, or energy-oriented approximation, where many of the problems we solve traditionally are then solved with a data stream of how much energy is my application using. The very big challenge in these kinds of systems is trying to scale to a shared environment. Pretty much every modern system that we think of is built on a shared environment. If you think of either hardware, software, whatever, they're all using some shared system, usually something like the Linux time sharing system. So the reason this is such a challenge is that applications that are run in these shared systems are going to experience energy entanglement. So inherently, any application can actually see the energy consumption of any other application. This has all sorts of potential pitfalls, but most importantly, it means that an application that may be run in the development site is not going to run the same in production. And so any sort of work you do to, for example, optimize your program for that kind of consumption, you may not be able to use those insights the way you would like to. So our goal is to then try to port these kinds of applications into a shared environment. So that way the development and deployment sites behave identically. So to achieve this, we are presenting eFlect, which is an energy virtualization framework. The idea is a lightweight framework that tries to avoid energy entanglement by doing everything at the application level. So there's no operating system modification. It's all understood of the application. This system is also customizable and can be extended to different kinds of energy sources. So our key idea is energy virtualization, which we then deliver a application the slice of its energy. This is done in a pretty simple way. We sampled the entire stack in order to, across the entire system, to detangle this energy consumption. So we just need to know the system energy. We need to know the activity of the system and the activity of threads, since that's the primary concurrency unit for how applications are managed, threads or tasks. So as a result, eFlect worries about the whole stack, and the end user doesn't have to worry about it at all and just get the energy reading that eFlect provides. So for example, if I have, some thread executing on some CPU, the energy on that CPU is 4 joules, the system is consuming 10 joules, and the thread is consuming, or not joules, sorry, 10 jiffies, which is the number of cycles consumed on a CPU in a Linux system, and the thread is consuming 5 jiffies. We can just take a ratio to get the energy for that application. So just some quick details about the design. So the idea behind it is that we get fine-grained temporal detanglement, since all of our measurements are done at millisecond intervals. We also are aware of how the threads are moving around, since we're tracking thread behavior. eFlect is decentralized, so no eFlect instant between different applications are coordinated. A single application is its own eFlect instance. As I said before, there's no operating system, VM, or hardware modification. And finally, it's customizable. So there's a public API, so it can be customized to different systems. I'm going to present some evaluation data just very quickly. This is done in Java on the Hotspot JVM over Decapo and one TensorFlow and a TensorFlow session using the Inception v3 graph. We use the RAPL system to get our energy information, and the Linux Jiffy system, Linux Jiffies from the proc system to get the activity of the hardware. So first, this is a plot of energy share. So the idea behind this is that the 2 stack lines are the 2 eFlect virtualizations. The green line is one instance of the ray tracer Sunflow, and the red line is a second instance stacked on top of each other. So as you can see from here, the energy is actually quite well balanced between these instances. where they both consume about 50% of the total energy. This is actually expected for Sunflow since this particular runtime maximizes all of the cores and uses as many resources as possible. So the two applications are competing for resources. In another case, when we're working with TensorFlow, TensorFlow, on the other hand, doesn't maximize threads. It just has a set number of threads for each of its instances. So as a result, both runtimes essentially choose a socket that they sit on and do almost all the work in that socket. You can see here that this green line, most of the energy is actually consumed by one instance in socket 1, and in the other case in socket 2, it barely consumes any. Oh, sorry, that's not supposed to be there. So finally, I'd like to present some case studies we did with eFlect to kind of demonstrate how it can be customized to and actually ported to a real application. So first, we have a case of energy adaptation. We maintain some energy SLA or some target so the application behaves in some way. We use a stochastic optimizer called Aeneas. In the case where we're not using eFlect, you can actually see that in the shared environment at the bottom, this is showing over some elapsed time the amount of energy consumed at each work unit. In the top plot, this is run in isolation. It's just a single application. So at the beginning, it actually is testing some some smaller configurations and increasing the energy as the configurations get adjusted to more complicated ones for things like anti-aliasing for the ray tracer for Sunflow. In the shared environment, you can see right at the beginning when it's doing its initial training, it doesn't actually know its energy consumption very well, makes a huge overestimate and struggles to converge. When we then add eFlect, we can see that in the shared environment, it early on is aware that it's not really consuming anywhere close to that much energy, and so it converges much more quickly. Our second key study is energy profiling, where we essentially assign energy to methods so we can get an idea of how a runtime is consuming energy. So for this case, we used a concurrency-aware profiler called Chappy. Without eFlect, we can see that this is a method ranking where it shows the % energy consumption for a bunch of methods in some runtime. This is for the benchmark H2, which is a database application. So in isolation, you can see that the top 3 methods are comparisons, binary search, and binary search. However, run in the shared environment, you can actually see that the second and third methods flip by a pretty significant amount. So that could be for somebody trying to look at this, they might have to figure out what exactly is happening or why is it switching. With eFlect added, we actually found that we are able to recover the ranking or get something much closer to the original ranking when we are able to decouple its behavior from another application run concurrently. And I believe that's all I have. Thank you very much.
Perfect, thank you. And now going back to our author from the 4th paper. I assume it works this time?
Yes, I think I can. Can you see my screen?
Yeah, it's coming. Yeah, perfect. Thank you.
Okay, cool. So, hi everyone. My name is Zhuangbin Chen from the Chinese University of Hong Kong. Today, I'll be presenting our paper entitled Adaptive Performance Anomaly Detection via Pattern Sketching. Nowadays, online services are everywhere. For example, Google Suite, Office 365, they have been increasingly integrated into our daily lives. Performance anomalies represent performance degradation issues of online services. For example, slow service response. They are potential threats to business revenue and customer satisfaction. To ensure the performance of online service systems, their status is closely monitored with various software and system metrics, such as request latency, traffic volume. Performance anomaly detection is to identify the observations that deviate significantly from the general distribution of data. Time series anomaly detection is a classic problem, and indeed, many approaches have been proposed in the literature. Compared to them, our approach can better meet production requirements thanks to the following advantages. The first is interpretability. That is, our approach can explain what an anomaly represents. Interpretability can help gain engineers' trust on the results and accelerate failure understanding. The second is the ability of online learning. Many existing methods need to retrain the entire model to accommodate unseen patterns and fight against possible concept drifts. Finally, our approach provides a way to accumulate human knowledge, which is a valuable asset for a company. Our approach is based on the key observation that an anomaly is dissimilar to normal data while similar to anomalies of its kind. In this metric time series where anomalies are in red, we can see normal data, the gray part, do not look like any of the anomalies, but we have two pairs of similar anomalies. Based on these observations, we have three main tasks. The first is to automatically extract metric patterns. By metric pattern, we mean there are multiple similar subsequences in this time series. For example, these four anomalies constitute two metric patterns, pattern 1 and pattern 2. Patterns like pattern 3, which are formed in normal periods. We can see a metric pattern can be either normal or abnormal. So in task 2, we need to distinguish them. These patterns can be used to quickly detect anomalies. Finally, we can label performance issues associated with each of them. By doing so, when a known pattern is detected again, we can immediately recognize what has happened. We call such a design pattern sketching. Our performance anomaly detection approach is called AD-Sketch. There are three main components in AD-Sketch. The first is metric pattern discovery, where we also conduct offline anomaly detection. This is like training a model with offline data. The second is online anomaly detection. This is like deploying your model in production environments, where metric time series. In this case, the parameters and data of your model are fixed. The final one is adaptive pattern learning, where the model gets updated when doing online anomaly detection. In the evaluation part, we address the following three research questions. That is the effectiveness of AD sketches offline, online, and adaptive anomaly detection. The results show that AD Sketch outperforms state-of-the-art approaches. Also, it has been deployed in production and demonstrated practical benefits. This is the end of my presentation. Thank you, and I'm happy to take questions.
All right, thank you. So maybe if we could get all the authors up here.
How do I stop the screen sharing? Okay.
There we go.
Okay, perfect. Just to let you know, Han will need to leave, but here I'm more than happy to answer the questions if you send here an email.
All right. So missing two authors, two more, if you'd like to come up.
Hello.
And do we still have, yeah, there we go. Wonderful. So thank you all for your presentations. We're approximately on time, not too bad. And I guess I'm gonna just start with just reading out some of the questions from the chat. The first question was directed to you, Masood. How did you collect the bug reports and the baseline of the search?
Thank you for the question. We collected bug reports from Bugzilla, the bug tracking system. And then we also collect the bug fix commit from the GitHub repositories. And then we try to match between the bug report ID and the corresponding bug fix commit. So sometimes the bug report ID is found on the bug fix commit. So using that linking, we constructed the ground truth. But for the baseline technique, so we use the pre-processed version of the bug report as the search query. And as the search engine, we use basically the Lucene BM25 implementation. So yeah, preprocessed version of the bug report as the baseline query and the Lucene as the search engine. I hope that answers your question.
Well, it's Lavinia's question, if you have a follow-up there. Or maybe not. And Masood, I think or do you?
Okay, so should I ask
Yeah,
any
if you'd
question?
like to ask your question of Yichan, yeah.
Okay, so I have this question to Ichan's. Sorry for the mistake in the pronunciation. So according to the clean code principles, Uncle Bob is suggesting that we are not supposed to introduce any kind of side effect whenever we are implementing the method, right? But the foo method that you presented, it is to some extent modifying the value of that input parameter. So can we avoid this kind of bug by just following the clean code principles? What do you think?
Can you repeat your question, or?
Okay, so
Okay.
you present, yeah, sorry about that. So you presented the method called foo, right? So, and in that method, the parameters that you are taking in the body, the value of that parameter is being modified, right? So that's a kind of side effect. Yeah.
I know. In fact, we have discussed this, the parameter choice in our experiment in our paper, and we didn't show that. We found that the parameter we set at something like 0.5 or 0.01 does not affect the result. In fact, we have tried some experiment on this.
Okay, thank you.
Does that answer your question?
Partially, I guess. Thank you.
Okay.
All right. I had a question here. So you guys mentioned that you did some dynamic analysis as well. So what was this
Yeah,
combination of static and dynamic analysis that you used?
Yeah, we use the dynamic analysis to get the trace, and from the trace we can take the data flow dependency, and we use the static analysis to get the control dependency, and we combine those dependencies into a unified model.
Okay. All right. Thanks. And next question, I think Masood, you asked this of Timur. So if you'd like to read out your own question.
Yeah. I think this is a very interesting talk. So since I do work with software bugs, so I'll be interested in the buggy behavior. So since Timur is working with the energy consumption, I was just wondering whether do you expect any kind of difference in energy consumption between, let's say, buggy version and the bug-free version of a software program? And if there is some kind of difference, can we really detect that? I mean, to what level? I mean, can we model the energy consumption up to, let's say, statement level?
So a buggy and a bug-free program are going to be different implementations inherently, even if the implementation might not be the same, if inputs are wrong, right? And you find a bug through like some sort of like bad input that you're dealing with, they will have differences in how they're consumed. Can we detect them? That is going to depend on the application, and it's also probably still going to require an expert to look and actually think about, okay, is this actually making sense how this is being utilized? So like in the case of Sunflow, right, one of the things you would expect to see from Sunflow is when you have two applications that are both maximizing as many resources as they can, they'll have competition, and so you should be able to see the competition between those applications. But if you have, for example, an application that, for example, if you think of something like GraphQL, that all it does, a lot of what it does is I/O operations, because a big data framework. Instead, you won't see much behavior from it. So it's going to depend on what the differences are between those. And so, like another example you can think of is for TensorFlow, the inception model, the difference between the version 1 and the version 3 models, same fundamental architecture, but totally different performance behaviors because they rearrange the network. And so are you going to see those same savings between the two networks if you account for the fact that one will run faster? Does it have a different energy profile? So you can detect some of these things, but it depends on what system you're using and what you actually have access to, because you need to get some sort of method information. And in our case, we're using something for the JVM hotspot specifically, so we get the call traces that way. So not dealing with something, for example, like trying to stop the entire GC to get safe points. So it's going to kind of be limited by what you have access to.
Yeah, interesting.
And I think Lavinia, you had a question for Timur as well.
Yeah, I can read my question.
Sure.
It's about what are the downsides to running only at the application level. I remember you said that is lightweight, that is a good thing, but what are the downsides that you need to catch on?
So the downside for the application level is really going to primarily be to the consumer, is they only will know what's provided by the interface. So in eFlect itself, it may know all the system information. It may know privileged information. It may even be a privileged process in some system that you want to deploy it in. But for the client that's consuming that data stream, that's the limitation, is what actual information are you delivering to them. And so again, it's part of it is to remove that normally you might see, for example, like RAPL's known to have like side channel leak issues. You can try to minimize that by going into the application level. So the downside exists more for the client than anything else, because they won't be able to see that extra information, which is both good and bad depending on who you are.
Thanks for the answer.
All right, and then what's the last question we have in the chat? I guess Lavinia, again, your question for Chuangbin Chen.
Okay, I was curious about if you have the opportunity to do a benchmark with industrial implementations of the type of detection. For example, Datadog that have anomalies detection for production.
You mean to build a benchmark of different anomaly patterns?
Not only for the patterns, but actually applications that try to do this type of things in the industry.
Oh, okay. You mean a benchmark of some different anomaly detection approaches?
Yeah.
Well, actually, that's one of the ongoing work. We are already come up with these ideas, and we are writing the paper and writing the code.
Okay, so maybe spoilers there.
Yes.
So, do we have any other questions from the audience?
Yes, I actually have a question for Masood.
Go for it.
So your paper is talking about some IR-based approaches, and I was wondering whether there are some deep learning-based approaches and how's their performance compared to the IR-based ones. Thank you.
I think that's a very good question. So there have been a few work on the use of deep learning in the context of bug localization. So they perform comparatively better, but one problem with that is it's a bit difficult to, let's say, construct the data set for a deep learning based technique. So for example, let's say if we are looking for some kind of classification problem, so we have the whole code base. So let's say I have a bug, so that is our test instance. And for that, I will have probably, let's say, only 3 files that is true positive, and the whole code base is kind of false positive. So there have been some work using deep learning techniques, but they face this challenge. That means oftentimes they try to construct the data set in such a way so that that data imbalance is to some extent, let's say, manually mitigated, right? So although they have very good performance, but they are suffering from this limitation. And on the other hand, the information retrieval based technique is not suffering from that problem. And yeah, so but study shows that in another of our work, we found that most of the bug reports actually contain some meaningful keywords, but the challenge that we have is that we still do not have intelligent techniques to identify those keywords effectively. So that is why I am focusing much more on formulating appropriate queries from the bug report rather than focusing too much on the deep learning based bug localization. Yeah, so that's, yeah. I hope
Thank you.
that
Wow.
answered your question.
Yes, yes. Well, I do agree because we also find that sometimes some rule-based or maybe simple machine learning-based approaches can do much better than the deep learning-based approaches.
Yeah, that's true. Thank you.
Any other questions here?
Well, I actually also have a question to.
Go for it.
So, actually, I'm to your area. So, can you elaborate on why in a shared environment, one application can affect the energy calculation of another application?
Sure. So the Sunflow example is a nice one because it demonstrates this well. So if I have if I have a single CPU shared by two applications, let's take two instances of Sunflow, and they're both CPU driven, so they're trying to do as much work as they can, they may end up being co-optimized. So as a result, however the instructions are then run is going to be based on trying to interleave those Sunflow operations. And so when you have this homogeneous situation, you can end up seeing these co-optimizations where the entire system is running at lower energy, running at a different energy value than it would in isolation. You can kind of even see that from our case study with the stochastic optimizer. In isolation, the application still is consuming up to 160 watts, and for a single application, so it's using as much energy as it can. When co-run, however, the entire system might still consume that many watts, but the specific application itself may not. And so when actually broken down, you can see that when you use all the system information, it does believe that, yes, I did actually consume way less than before, even though I've done the same work unit. And so the access to resources you have changed, and as a result, the amount of energy you're consuming on those systems have changed. So just because one of the issues is energy is temporal in nature. If I take an energy profile end to end for a work unit that's 5-6 seconds long, I'm not actually going to know how the energy was distributed over the entire time, because there's an order to which things happen, and that is inherently going to change power consumption.
Okay, I see. Thank you.
Have other questions from the audience? We still have a few people here. If you'd like to unmute yourself and show up.
I actually have one more question to Timur.
Go for
So
it.
it's a kind of clarification question.
Sure.
So how are you capturing the energy consumption report from different devices? So do all those devices, so let's say CPU, do they have any kind of log that you are accessing, or how you're actually capturing that energy consumption data?
So for the case of a Linux system, we're using Intel's RAPL interface, so the running average power limiting interface, that reports counters that reports the amount of microjoules consumed since last boot time, like the total amount. And so if you take a forward difference of two samples taken, some T1, T2 apart, you'll get a power across that time range. So that's going to give us the energy measurement specifically over some time interval. And so if we're sampling at some periodic rate, then we'll get much finer granularity than if I took two samples end to end for a workload. And then we do something similar for the system activity. So we leverage the Linux's proc system. So the proc pseudo file system reports all of Linux's behaviors and what's going on in the system, and system information. In addition, there is procstat, which reports the current CPU statistics. So it reports jiffies. Jiffies are the number of cycles in some unit. So for most systems, jiffies essentially are the number of cycles at like 10 hertz, at 100 hertz, sorry, 100 hertz. So it should be 10 millisecond intervals is when that's being updated by the system. And so those pieces of information allow us to get these ratios of how much energy a specific task consumed, because Jiffies are reported not only at the CPU level, they're also reported at the task level. So Linux itself organizes an application as a process, and all of its threads are called tasks. So as a result, that's how we end up getting the mapping back to the actual application, by taking all that information about its children.
Yeah, thank you. Very interesting.
I have an answer for myself. I didn't see the question in chat before. In fact, for a function, the data flow will pass from the parameter to the final result. If you don't modify the parameter but use another variable, I think it should be the same. Does that answer your question? Hello, Masad?
Oh yeah. Oh, sorry about that. Yeah. So can you repeat the answer? I was not following properly. Yeah.
You mean the following property?
Yeah. So I actually did not get the answer. So yeah. Can you repeat a bit? Sorry about that.
Yes. I think, in fact, for a function, the data flow will pass from the parameter to the final result. And if you don't modify the parameter but use another variable, it will be the same. If you don't modify that a but use something like int x equals to a and modify that x, it should be similar, I think. So such things will also happen.
Yeah, so the value of that input parameter was stored on the same, I think on the same variable. So that was my question. So this is how, so that means when a method is done with the execution, the input parameter value should not be changed. So I was just quoting Uncle Bob, so I could be wrong, right? So yeah, maybe.
Yeah, but if you want to use that variable and the value of the data flow is just following from the parameter to the final result. Yeah, it does not use something other variable. It will just go through it. You get that?
Okay, I think we can discuss after this session in more detail offline. Yeah, thank you.
Okay, thank you.
And anyone else here with any other questions?
Maybe I will do one more. So my question goes to Yiqian. So if in the if statement it's another complex statement, for example, a function call, how would you deal with this situation, and would it incur a scalability issue?
In fact, for something of complex statement like a plus b plus c plus d, we did our implementation is inside at bytecode level, so such long statement will not affect the result. And for something like function call, we will also trace the call function, so we can just have something like assignment at the start of the function call. We assign the parameters of the new function, and the return value is also from the data flow. So we just trace all the things.
Okay, I see. Yes, thank you.
Timur, there's a question for you in the chat from Kevin. He
Yeah.
asks, well, you can probably read it and
yeah. I read it. I was typing. I can verbally say something. So, I would have to double check correlation specifically for more threads. What was more important was whether as how much an application actually used the CPU, since we're looking at Jiffies, and that's what we're looking at. So for example, if I have an IO bound program, Jiffies is not going to report that information. So the database application H2, for example, is IO bound. So some of that information is not going, some of what's actually happening in the actual computations it's doing is not going to be reported that way. So the number of active threads I'd have to check, but I don't believe that there's a direct correlation with that. As far as scalability, our artifact data actually has, we ran cases with 2, 3, 4, 5 different instances of applications homogeneously, as well as some other heterogeneous studies, mixtures of different applications. And it doesn't seem to impact eFlex ability to maintain the virtualization. As we scale up, as we go to 5 applications, especially in the case of Sunflow, where there's tons of competition conceptually, we're still seeing everyone gets a equal-ish share of about a fifth or a fourth, or co-instances. So there doesn't seem to be a significant notable impact when we start scaling up a lot compared to just 2 applications. And for something like Sunflow, that's a enormous amount of load, since it's such a big resource consumer.
All right, thank you. And any other questions? Last chance here from anyone. If not, I do want to actually ask one, and that this kind of goes to all authors here, because I work in industry now, in industry research. So my question to all of you all is, how do we apply your research or your technique in the immediate future? And would you like to spend a minute just talking about that, each one of you? And we could go in the same order in which you presented.
Yeah, I think that'll be me. Thank you, Anant, for the great question. And this is something we have been also wondering for a while. So the IR-based bug localization, information retrieval-based bug localization. So there have been some recent survey with all the major companies. I think that was done by the group of David Lowe in 2018. So what they come up with is that the performance of the information retrieval-based bug localization technique is still not up to the acceptable level to the industry for the industry, but industry people value the automated bug localization. So they surveyed about 10 different bug management activities, and according to that survey, automated bug localization is ranking the first, according to the developers. So what we are facing right now is that low quality bug report. And when we have low quality bug report, then the information retrieval technique is to some extent suffering. So that is why we are using different kind of query reformulation technique to improve the search query for that IR-based technique. So right now I am trying to use different keywords from the bug report using different kind of query reformulation techniques. Then there are also other techniques that are extracting keywords from other complementary sources like source code or past bug report or bug fixing history. And this is how we are trying to improve the query so that the IR-based bug localization is more effective. So we are still not up to that point, but there is a threshold from the industry. That is, you have to achieve 75% hit at 5. So we are not there yet, but we are striving. And hopefully in the next 5 to 10 years, we'll be able to present something to the industry. I hope that.
Yeah, I mean, yeah, we care more about true positives than false positives, right? It's
yeah, it makes sense. Yeah.
Moving on, Yuchan, if you'd like to.
No, in fact, the industry can directly use photo localization technique, I think, but we need to, but we need better implementation and infrastructure, I think. So this is something more detailed about the coding detail. Yeah, we need better implementation.
Yeah. All right, and moving on. Zhuangbin, even though we flipped orders.
Okay, sure. Well, I actually suggestion that is work at the company by yourself. Well, I actually have the opportunity to work in a company, and I found that the best way to apply your algorithms techniques to the company is work there and talk to the on-site engineers so you can know their pain points. You can, you will find out that we care about different things. For example, we as researcher maybe care more about fancy ideas, but they only care about the effectiveness of the approaches. and they can be simple, but it doesn't matter. So just if you have the opportunity to work in a company.
Absolutely. I'd encourage that too. And Timur, last up.
Sure. I guess in my case, it's more